right, back at it. I hope that your answer is ready to check now that you've started the video lessons up again. We were asked to determine the empirical formula for a compound made of 75.7% by mass of the element tin. Its atomic weight was provided right off the periodic table of 118.70. And the rest of that would be fluorine, so 100 minus 75.7% gives us the rest of the percentage by mass of fluorine. So that was where the 24.3% by mass came in. So assuming 100 grams of the sample, those mass percentage, just simply change the percent sign to grams. We're being asked to find SN something, F something, where those somethings are whole number mole ratios. So we have two elements in our list. We have to take each of those elements and convert them to moles. That's what we call our pseudo formula. Divide those moles by the smallest number and work it into a whole number mole ratio. So applying our conceptual plan, each one at a time, we're taking the mass of individual elements and turning them to moles. 75.7 grams of tin divided by the 118.70 gives us a mole value of 0.638 of tin. Moles of tin, grams divided by formula weight. Do the same for the fluorine. 24.3 grams, and again, just to reemphasize, 100% of the mass, 75.7 of it comes from tin. The remaining percentage, 100 minus 75.7, is where we found the mass of fluorine. 24.3 divided by the 19, its given atomic weight turns it into a mole number. So we have SN 0.638, F 1.28. We called that a pseudo formula. We can't leave it like that because we know subscripts are always whole number ratios. You divided each by the smallest number, and generally this is true. They work to a whole number ratio. Fluorine is twice that of tin. So our formula, SnF2, just as the name implied, stannous is another name for tin 2 fluoride. SnF2, the charge on tin, plus 2, charge on fluoride, negative 1. We crisscrossed, and we can verify that the name indeed matches the formula. SnF2 is tin 2 fluoride. Common name there is stannous fluoride, Latin name for tin. Try another. Determine the empirical formula of magnetite. It contains 72.4% by mass of iron, and the rest of that coming from oxygen. Well, they're just making us do a little 100 minus 72.4 to determine the mass. I highly recommend pause the video, work it out, and just double check your answer. Given the mass percent of iron, we find the percentage of oxygen. We understand that those percent signs directly change to grams. Convert each gram into a mole by dividing each by its atomic weight. Those mole numbers will then be divided by the smallest of the two to find your whole number ratio. When you applied your conceptual plan, the number of moles of iron you found by hitting 72.4 divided by 55.85 grams, 1.30 moles of iron. When you hit for oxygen, its mass of 26.7 divided by the atomic weight of 16 was 1.73 moles of oxygen. What's the smaller of those two values? The 1.3. So when we divide each by 1.3, we're working to find our whole number ratio. We can't leave it with decimals, so we divide each. And this one gives us a ratio of 1 to 1.33. What's that 0.33 repeating itself? What is that fraction? Well, that represents a third, doesn't it? 0.3 repeating itself is the fraction 1 over 3. That tells us to get rid of 1 over 3, we triple it. Tripling gives us a formula of Fe3O4. Fe3O4. Did you find that when you practiced? Boy, I hope so. We've worked through many examples of how we can turn percents into grams, grams into moles, and therefore find an empirical formula. The empirical formula is the lowest subscript ratio possible. We understand that molecular formulas are the true formulas, the way that we find it in nature. It's typically some multiple of the empirical formula. Now, it may match like water, H2O. That's both the empirical and molecular. But if we do need to multiply that empirical formula by some factor to find its molecular formula, we simply multiply it by the factor we call N. What's the target molecular mass of our molecular formula? What's our empirical formula mass? And see what that multiplying factor ends up to be. Let's take an example and make this make more sense for us. Let's find a molecular formula for a compound called butane dione. Now, again, that is an organic molecule, a completely different beast. We are in inorganic chem, orgo, a whole different class. So that would not be something you'd have to know. But given the empirical formula, we could definitely find its molar or its molecular formula. So this is given. C2H3O. 2 carbons, 3 hydrogens, 1 oxygen. That is given information. You would by no means need to know that by heart. Also given, the molecular mass, that's MM, molar mass or molecular mass of our target formula, is 86.03 grams per mole. An empirical formula, C2H3O, that when I multiply it by some factor is going to give me the target weight of 86 grams. Let's add to see what is the empirical formula weight so far and see what multiple 86 is of that. So the molar mass of our molecule divided by the empirical molar mass gives us this factor N, which we distribute through the subscripts. Well, what's the formula weight of our C2H3O? Add up a couple of carbons, 3 hydrogens, and 1 oxygen. 2 carbons, 3 H's, and an O. If I add the formula weight, 2 carbons plus 3 hydrogens and 1 oxygen, see how they're getting 43.04? If the target weight is 86 and the empirical is adding to 43, what multiple do we see? Well, if 86 divided by our 43 gives us a factor of 2, we need to take the empirical formula and make it twice as heavy. To make it twice as heavy, we distribute a 2 through the subscripts. So C2H3O simply becomes C4H6O2. The molecular formula, C4H6O2, the way we find it in nature, butadiene, C4H6O2 adds to 86, and yet the subscripts reduce down to the original 2:3:1 subscript ratio. So the steps, given an empirical formula and a target mass, simply see how many times that the empirical formula weight goes into the target weight and distribute that number through the subscripts. That easy. Molecular mass is the true formula. Empirical mass is the lowest subscript ratio. Benzopyrene has a molar mass of 252 grams per mole. Its empirical formula is C5H3. What's the molecular formula for benzopyrene? Add up the empirical formula weight and see how many times that goes into the target of 252. Distribute that number through and see what we find. If C5H3 has 5 carbons and 3 hydrogens, let's add up the empirical formula weight and find that to be 63.08 grams. We know that the target weight for the molecular formula is 252. How many times did that empirical weight go into the target weight? 252 divided by that 63 showed us a factor of 4. Did you distribute a 4 through your subscripts and find C20H12? The molecular formula for benzopyrene, C20H12, adds to the target of 252 and yet reduces down to a simpler ratio of a 5:3 subscript ratio of C's and H's. Sometimes when we calculate empirical formulas, we are given combustion analysis. To combust, taking a hydrocarbon, adding oxygen, and adding all kinds of heat and light energy, coming out is the carbon dioxide and water vapor. So this is generally used for organic compounds. When we combust, it's a hydrocarbon, some type of fuel, like gasoline we combust in a automobile engine to move from place to place. Major component of gasoline is octane. It's a hydrocarbon. As we add oxygen and burn the fuel, we release carbon dioxide and water. So by knowing the mass of the product and the composition of those constituent elements in the product, the original amount of the constituent elements can be determined. So when carbon from our fuel forms carbon dioxide, the only source is coming from the original fuel. All of the hydrogen that goes into the water came from the original fuel. And that original mass of oxygen is found by subtraction. So we need to work out with combustion analysis all of the masses of the constituent elements, C's and H's and O's, and then the straight math as we've done before. Grams convert to moles, divide through by the lowest mole number, those become the subscripts of our empirical formula. Combustion analysis just is a little more work, a little more detective work to figure out the mass of each individual component, C's and H's and O's. So we have this is just a schematic of what combustion analysis allows us to do. In the first, we take this fuel. Notice there's a sample inside of a furnace that's burning. So anything that burns requires oxygen. This is some hydrocarbon sample in a furnace burning in the presence of oxygen. They collect water vapor first and weigh it. The remaining gases go into a carbon dioxide absorber and they weigh it. And everything else that passes through is just considered other substances that's not absorbed. So by combustion analysis, we're able to get a weight of water and we're able to get a weight of carbon dioxide. And simply using mass percentages as conversions, we can pull out the weight of C's and H's and O's and therefore determine the empirical formula of our hydrocarbon fuel. I'll go through it slowly, step by step. We have a combustion of 0.8233 grams of a sample that contains carbon, hydrogen, and oxygen. It's produced by the following. Carbon dioxide, 2.445 grams, was absorbed and recorded as a weight. The water was collected and weighed to be 0.6003 grams. Here's what we're saying. I know the weight of carbon dioxide, I know the weight of hydrogen, and I know the weight of the original sample, composed of C's and H's and O's. That's all we need to determine the empirical formula step by step of our compound. Now, look at carbon dioxide. It's made of C's and O's. We can use a percent by mass of carbon dioxide to pull out carbon's weight. We'll do the same strategy for water, pulling out hydrogen's weight. And the difference between the mass of carbon and hydrogen and the original sample must be that of oxygen. That missing mass is the third element, oxygen. So let's start by writing down our given quantities along with its units. The entire compound that's composed of C, H's, and O's, the total weight of our compound was 0.8233 grams. After combustion, we collected and weighed carbon dioxide, 2.445 grams. And another product was water vapor. They collected and weighed at 0.6003 grams. We want to know the empirical formula, C something, H something, O something, where those somethings are called subscripts, and those will be whole number mole ratios. If 2.445 grams of carbon dioxide and 0.6003 grams of hydrogen, that mass data has to work into mole data, which then goes into an empirical formula. Let's look at a conceptual plan. I have to clear my throat. Sorry. Grab water. Thank you for your patience with that. Our conceptual plan says, knowing the mass of CO2 and the mass of water, we can find mole numbers. From mole numbers, we can convert into element moles. And from there, we can find grams and work into subscripts. With a conceptual plan, we can take the mass of carbon dioxide and the mass of water and work out into the individual element mass, C's and H's, and the missing ingredient there must be the mass of the oxygen, that's why it's a different color. From moles of O, moles of C's, and moles of H's, we'll be able to divide through the smallest number and find an empirical formula. So many steps it might seem in this schematic, and yet it is actually quite easy. That mole ratio becomes our empirical formula. Take a minute and digest this slide before I click it on. Just study it a minute and see what you think of the pathway we're about to take. We're given grams of CO2. We're given grams of water. We'll convert grams into moles of the compound. Those moles will be converted into moles of each element and back to the grams. The missing weight from the original sample with the combined weight of C's and H's must be the oxygen mass. And we can also then use that to convert it to a mole. That top line is all that's necessary to do a problem just like we worked before. Once we know mole numbers, we can write that pseudo formula just as before. So let's begin the journey and just show you step by step how to process. Let's write down what we know. We have all of these relationships. We're going to need some formula weights. Adding up a CO2, 1 carbon with 2 O's gives us an atomic weight 12, and oxygen at 16 apiece gives us 44 grams. 2 H's and an O when added together give us 18, the atomic weight of hydrogen 1, oxygen 16, so that gives us 18. We know the mass of a single carbon, and we know the mass of hydrogen. So these are just collected relationships called molar masses. I call them formula weights, whatever you like. So gathering the data right off the periodic table to just do our gram to mole conversions. Alrighty. When I look at my carbon dioxide formula, notice that it has 1 carbon. So 1 mole of carbon dioxide is equivalent to saying 1 mole of carbon. But in water, we have 2 H's and an O, 2 hydrogens for every 1 water molecule. So just considering that when we set up our mole ratio of H's in the water molecule. We'll begin by calculating moles of carbon and hydrogen. When I consider how to do that, we start with a mass and we convert it to a mole. 2.445 grams of carbon dioxide divided by its molar mass of 44.01, and seeing that ratio of 1 carbon in the formula of carbon dioxide, converted it to 0.0556 grams, 0.556 moles of carbon. Same journey, but now for hydrogen, starting with what we were given, the mass of the water. Converting the mass of water into moles of water, we use the formula weight of H2O. Notice that we had mentioned in the formula for water, there's 2 H's for every water. So that second conversion shows 2 moles of H in every 1 mole of water. There's 2 H's in a water molecule. 0.0662 moles of H. See now how we've identified the number of moles of each of our carbon and hydrogens. We need to get those back to grams. So I'm going to simply take each mole number and multiply by its atomic weight. So the moles we just recorded now multiplied by its atomic weight. Mole times formula weight gives us 0.6673 grams of carbon. Same strategy for the hydrogen. Take the mole numbers that we calculated. Notice that when I multiply by atomic weight, we have moles canceling and converting to grams. 0.6673 grams of carbon, 0.06715 grams of hydrogen. Now what else do we know? There's a third element in our compound from the original story problem, oxygen. But that's easy to find. Remember how the given quantity of the compound was 0.8233 grams? We determined the mass of 2 of the 3 elements. The total mass of 0.8233 minus the sum of the 2 parts we know, carbon and hydrogen, leaves us with the 0.0889 grams of oxygen remaining. So the 3 parts added together give us the whole. 0.8233 total mass provided as a part of the original story problem minus the sum of the 2 elements we'd already determined leaves us a net of 0.0089 grams. Subscripts are mole numbers, so therefore we divide by the atomic weight of oxygen and find its mole. Now, after this work, we really have everything we need to write a pseudo formula. That pseudo formula is C something, H something, O something. Well, those somethings are the mole numbers we've determined so far. We've determined the carbon moles, the hydrogen moles, and the oxygen moles. Write them into a pseudo formula and see what we have so far. We have C, 0.05556 moles, H, 0.06662 moles, and 0.00556 of the oxygen. Pseudo formula because we can't leave them as decimals. What's the smallest number of those 3? The oxygen. Divide through by the smallest and see what you find for a whole number ratio. And you will have your empirical formula. When you divide through by the smallest number, did you find a formula that gave you all whole numbers? C10, H12, O1. C10, H12, O. When we calculate an empirical formula from combustion analysis, we have more work to do in the sense that we've got to pull out that information using percent by mass of carbon from carbon dioxide, using percent by mass of hydrogen in a water molecule, using percent by mass as a conversion factor to find carbon, and using percent by mass to find hydrogen from the water enables us to find the grams of those individual elements. And by a simple subtraction, we're then able to find the missing mass of oxygen, and the procedure becomes just like the others. Let's see what's next here as I try to shut off my cell phone. Sorry that it rang. Oh. Here's a problem that we can pause the video. Let me get my phone collected here. And the smell of dirty gym socks is caused by a compound, caprioic acid. Combustion of 0.844 grams of caprioic acid produced 0.784 grams of water, 1.92 grams of carbon dioxide. The molar mass of caprioic acid is 116.2 grams per mole. What's the molecular formula of caprioic acid? Boy, lots to digest. Spend some time pausing the video. Don't just play ahead. Pause the video, work through it, and start up when you're ready to check your answer. All right, let's see what we have. By combustion analysis, we're going to turn the grams of carbon dioxide into moles of carbon. 1.92 grams divided by the molar mass. There's 1 carbon in every mole of carbon dioxide. You found 0.0436 moles of carbon. Same strategy using the water. 0.784 grams of water divided by water's formula weight, and taking into account that there's 2 H's in a water formula. 0.0870 moles of hydrogen. Canceling the gram unit, step 1. Canceling the mole unit, step 2. Now we can easily convert each of those moles into grams. Take each of the moles of those elements and multiply by its atomic weight. Moles then cancel, and you've converted into each of the grams. We do that so we can add the 2 weights together. Carbon's weight plus hydrogen's weight added together, taken from the total of 0.844. The whole compound was 844. Carbon's contribution 0.524. Hydrogen's contribution 0.0877. What's the missing mass? Well, that must be of the oxygen. So when we find the mass of the oxygen, we can begin converting it into moles. Just tabulating in a table form here, grams of each of the elements and moles of each of the elements allows us to keep better track of each of just the data in the presentation. If the mass of the carbon, 0.524, the mass of the hydrogen, 0.0877, total weight was 0.844. That missing mass must be that of the oxygen, and it comes out to 0.232. We also need the mole of that number because subscripts are mole numbers. Grams divide by formula weight gets me into a mole. That's just a mole map problem. From the scale into the mole, we divide by atomic weight. See how the grams cancel out, and you've converted to a mole. So now we have the individual mole numbers. This gives us what we call our pseudo formula. C, 0.0436, H, 0.0870, and O, 0.0145. What's the smallest number? Well, it's oxygen. Divide through by the smallest number and you find what we call an empirical formula. The whole number subscript ratio, C3H6O. But we weren't done, friends. We weren't done. That's called its empirical formula. What was the target molecular mass of our compound from the original story problem? We had another little piece of data provided for us. The target weight, if you recall. The target weight said when we were done it had to be 116.2 grams. So far, the empirical formula weight is adding to 58. So we weren't done because our empirical formula wasn't heavy enough. If the target weight was 116 and the empirical weight was 58, we need to double our subscripts. By doubling our subscripts, we make the molecule twice as heavy, giving us that target. C6H12O2, our molecular formula. C6H12O2 adds to the target weight of 116 and yet reduces down to the subscript ratio 3 to 6 to 1. Good work! I hope you worked through that and found success.